All right, welcome to this new video. In this case, I would like to keep it under 30 minutes and give you a brief introduction into large language models, going into detail into how do we actually build these models, highlight what they're really good at, but also expose some of the flaws that they still have. Now, the motivation for this video is that even if you work in the field, it is not always easy to keep up with everything that is happening, and equally it's not always easy to cut through what is hype and what is reality. So here on the 6th of January, we had Sam Altman say, "We are now confident that we know how to build artificial general intelligence. Hence, we are actually turning our focus on super intelligence." And while these claims are exciting, they definitely don't go without criticism. There are people on Reddit saying, "Oh, you guys are so easily impressed by all this overhype." There is, for example, Francois Cholet, who has often been critical of some of these AGI claims. And he says, well, we can only say we have reached AGI if it's no longer easy to come up with examples that people can solve easily, but AI models struggle with. There were, again, especially around Christmas last year, there were all these headlines of whether the tech industry is once again at this AI slowdown, and lots of people are questioning whether in this Gartner hype curve, we might actually already be beyond this first peak. And specifically for OpenAI, I found this one Reddit post very funny because it said that OpenAI is really built on genius PR. There are so many people that are dissecting the tweets, these cryptic tweets that people from OpenAI sometimes send out, creating both fear but also excitement around everything that is happening. Now, the other thing to mention is that even if you are pretty positive about these technologies, which I myself am, it is not always easy to see the forest through the trees. There are so many solutions that are out there and new ones are coming up every single day. It's not easy to choose which one you're going to use, but it's not even easy to know for which specific use case you should be using AI and where you might better skip it. At the same time, LLMs really did not necessarily get much easier to use, as is noted here in a blog post. It's not always easy to make them behave as you would like them to. So what I would like to do with this video is somehow demystify a little bit the magic around AI and really go into detail into how is the model constructed, what is the data, and how do we perform the training over this data, and then zoom into what are the model abilities, but also really what are still some of the limitations that they have, which may actually be limitations that are really fundamental to the specific architecture that we're currently using. So we will start it off slowly. We will start off with the basics, the prompts. If you've ever used ChatGPT, this window should be familiar to you, and where it says currently message ChatGPT, this is the place where you would usually put in your little prompts, the thing that you want the model to help you with. And this can be anything from, oh, give me a simple recipe for pasta, give me ideas what to do on a Friday night, ask to write an email for you, suggestions for where to get vitamin D, because in London it is very hard to find it in the winter. Or you could even, dump in a bunch of text messages from your boyfriend or girlfriend asking the model, what do you think? Does he still love me or not? Now let's dissect a little bit what happens to this prompt once it goes into the model. If everything goes right, the model should output you with your reply, which in this case might be, well, sure thing, here is a recipe for a quick, delicious, fuss-free meal. And the way the model differentiates between what you're saying, what I'm saying, versus what the model is replying is that it puts what I'm saying into these user tags and whatever the model is replying into these assistant tags. And if you're simply using the model through this chat interface, you might not know that behind all of this, there is also a system prompt in these system tags. And this system prompt actually instructs the model how it should be behaving. If you're using it through an API, you can actually change the system prompt yourself. But if you're using it through the chat interface, this is something that is already decided by the model providers. And this is, for example, the system prompt from Claude, one of the models from Anthropic. And it basically says information of how the model should be behaving. So saying, the current date is this, your knowledge base was cut off on this particular date. If someone asks you simple questions, please give concise responses. If someone asks you controversial topics, don't try to provide careful thought, yada, yada, yada. Kind of really giving the model some more instructions on how it should be behaving. So once this prompt goes into our model, so let's start with here, prompt in the morning, I like to drink. This will be the example that I use for the next couple of slides. What happens first is that the model, when processing this, it will actually split this big sentence into so-called subwords or tokens. In this case, it might split in the, morning, I, and so forth. And here you might stop me and say, hey, but why are we actually splitting it into these subwords? Why not, for example, into letters? Or why do we do this split even generally? Now, if we think about splitting it into letters, we would have a much longer sequence. So partly splitting it into subwords comes from an efficiency argument where we would like to keep the thing that we're processing a little bit shorter. The other reason that we split it into these words and don't just work with exact sentences or letters is that somehow these subwords allow us to capture the semantics of the text in a better way. After we have these subwords, they get transformed into numbers because the numbers is what our model likes to work with. And specifically, things get translated into this sequence where every number is this ID that corresponds to where in the model vocabulary this particular token lies. So for completion, this model vocabulary is essentially the set of all these tokens, all these subwords that the model is recognizing and is able to process. After this little process of splitting it into subwords and transforming it into integer IDs, we are left with this sequence of integer IDs, and this is then what gets processed by the model, and finally also what generates the output that we would like. Now first, before I go into detail what we actually input into this model, I would like to say what is this specific output that we would like to get from the model? Or specifically, what do we even train these models to be doing? Essentially, what we train these models to be doing is to output the next word. So in this case of I like to drink, the next word or token might be coffee. And this coffee is what I'm training the model to correctly predict. And the way I do it is I show the model different kinds of partial sentences over and over and over and over and over again, and have the model guess what it thinks should follow for each of those sentences. Now, if the model makes its guess correctly, I update its model parameters such that it reinforces this guess, telling him, look, you were correct, keep it this way. If the model, however, was incorrect, so it incorrectly guessed what should be following my partial sentence, I adjust a little bit those model parameters so that it can learn from the mistake that it made. Now, let's go into what happens to this sequence of numbers as I actually pass it through the model. So first, we will transform this sequence of numbers into a set of vectors. Why vectors? Because they will again allow us to capture somehow more nicely the semantic meaning of each of those subwords. And the way we do this is through a first embedding layer. Once we have this, we have a bunch of different layers in our model. And what each of those layers are doing is essentially just transforming in some way that will hopefully towards the end of our model, so when we get the output, correctly be predicting what should follow our sentence that we gave into the model. So at each of those layers, these vectors are getting transformed in a particular way. And the way these are getting transformed is really governed by these model parameters. And this is, again, the thing that we can update in order to make sure that we're getting the desired outputs from our model. Once we reach the final layer, let's look a little bit at what the output in this particular layer is. What this layer outputs is actually the probabilities of how likely each of the words in our vocabulary is. So specifically, if we look at the very final vector that we had in our sequence, it basically outputs the probabilities that how likely is the next thing that follows in the morning I like to drink, how likely is it tea, how likely is it, for example, orange juice, or how likely is it coffee. And if the model is again learning correctly, it should assign the highest probability to the correct token, which in this case is coffee. The other way to think about this in a little bit more of a high level way is that we basically start again with this sentence, these sets of tokens or subwords in the morning I like to drink. And what happens through all of these layers is that each of those tokens gets transformed in some way. So each of these layers somehow slightly changes the meaning or the specific token that particular element is representing. And again, to highlight what we want in the final layer, we would like the model to somehow converge to tokens that follow the particular token that we gave the model. So the first in should at some point converge to the, in the should converge to more, and so forth until in the morning I like to should converge to the final token, coffee. So for each of those sequence elements in our sequence, we basically make a prediction of what should follow it. Now, there's a lot of details that I can tell you about how the model actually works. So how specifically do these transformations work? But I don't want to do that because then we will get into way too mathematical things. I would like to keep it very high level and point out two specific things. The first of which is the attention mechanism. Really one of the core features that's kind of like led to this boom of large language models working as well as they do. And what attention basically allows us to do is whenever we are computing the particular prediction, so whenever in this case we're trying to predict what should follow in the morning I like to drink, what the model is able to do is it's basically able to shift its attention to specific parts of this sentence in order to somehow predict what should follow it. So whenever it's, for example, predicting coffee, what might be reasonable is for the model to very much pay attention to morning and to drink, and use these two tokens to then somehow infer that a sensible follow-up might be coffee. So essentially, whenever the model is making its predictions, it is variably paying attention to specific words or tokens in the sequence that we're giving into the model. And this results in a very rich but also a very efficient way of capturing the different meanings that we have in our model. The other thing that I would like to mention is actually positional encoding. So when you're looking at this sentence, you see that in the morning there's a particular ordering to this sentence. So morning follows in the, drink is at the very end. But what the model sees is it sees all of these as a kind of bag of words. And the only way that we can actually tell the model what the order is that we basically have to embed or add these vectors to these token embeddings that tell us where in the sequence was each particular token actually lying. And it's a bit of a funny thing, and it's a bit of an artificial way to actually tell the model about these positions, and also how you specifically do this. There's a lot of work that went into doing it efficiently and accurately. Now that we know at least a little bit what these models are, I would like to also make a distinction between how big certain models can be. So the number of parameters, these little these things that we can update in order to make the model do what we like to predict the correct token, varies a lot across different models. So we have everything from very small models such as the small LM or the Meta Llama 3.2 models, which have around 100 million to a billion parameters. It sounds small, but in principle, a billion parameters is still a lot. But we have this all the way to really something around like trillions of parameters that people hypothesize that OpenAI's GPT-4 and Claude's 3.5 Sonnet actually have. And there is also a distinction here between closed source models and open source models. So closed source ones are the ones for which we don't exactly have the model parameters, and all we can do is just query the model and have it give us the output for the prompt that we put in. But for the open source models, they actually completely open source the model weights and sometimes even all the train data that went into these models. So there's a big range of sizes that these models have, and obviously also performance is very much dependent on how big or small the models are. All right, so I already said that whenever we are training the model, we are basically passing in a lot of different sequences in order to teach the model to predict what should follow each of the sequences that we pass in. And the thing to stress here is that when we are training these models, we really are passing in a lot of these sequences, typically something around billions or even again trillions of tokens, so of these subwords that we give into the model. let's look a tiny bit more at what specifically this data is, because this will also give us very critical insights as to where we can expect the models to perform well versus where they might not necessarily. So the first thing that goes into these models is, for example, very general internet data. This is really what also started these large language models, is that people were just scraping the web, for example, in these come and crawl snapshots, cleaning this data with a lot of different deduplication and filtering steps, because again, clean data is really very critical for these models to work well. And basically training these models on all these different things that we could find on the internet. There's also a specific data set called Fine Web Education, which contains a specific subset of more educational web samples. And the way, again, what data you choose would really define where your performance will be good and where it wouldn't. There's also a lot of domain-specific data that goes into these models. For example, there's the Stack, which is a data set that contains a lot of different code sourced from GitHub. Covering 358 different programming languages. And there's also MathPile, which contains a lot of mathematical reasoning data sets. What also got popular in recent years is to actually use synthetic data. Now, partly because, there's only so much internet data that we can find. And this, in a way, I see this as having been popularized by Microsoft's Phi 3 model, which in their report noted how they used synthetically generated textbooks and exercises which they generated with a much larger model, GPT 3.5, and used it to train a much smaller model. So to be very precise, in terms of this training data, what goes into these models, it's really a lot of content from anything such as blogs like Substack and Medium, university websites, MIT, Stanford, Wikipedia, a lot of LibGen data. LibGen is this archive where people post ebooks. So a lot of books have gone into the training data. And the reason I want to highlight this specifically is that whenever you think these models are performing a particular task really, really well, it is impressive from the model's side. But one thing to really stress is that part of their creativity and expertise also really comes from the fact that they leverage the work of other authors in books, in blogs, whatever, to generate their responses. Now, this is what we train things on. And now I want to spend a little bit of time on explaining also how do we actually evaluate these models. So I told you that we train the models to optimize the next token prediction, so to somehow correctly say what should follow a particular sequence that we input into the model. This is, however, not directly how we evaluate them. We actually evaluate these models on all kinds of different benchmarks that are designed to somehow measure the model's knowledge and abilities across different domains. So some examples, for example, the MMOU benchmark, which tests the model on different questions across 57 subjects in STEM, in the humanities, in the social sciences. There's a benchmark called HellaSwag, which tests common sense reasoning, whether the model would, for example, be able to pick the correct ending following a particular context. GSM HK8K is a popular mathematical reasoning benchmark. Human Eval contains a bunch of different programming challenges that we assess these models on. So we don't just assess them on predict the next token for these sequences. We kind of structure different kinds of problems in different kinds of domains to capture whether the models are properly learning what we want them to be learning. And whenever you see new models being announced, you will also see lots of tables or graphs like this, where basically they compare the newly announced model's performance across all these different benchmarks like MMOU that I just mentioned, to then say, oh, look, our model performs better compared to all these other models that we have. And again, the thing here that I would like to stress is that another big challenge really lies around contamination. So we are assessing these models on these evaluation benchmarks, but at the same time, trillions or at least billions of tokens go into our training data set. And who is to guarantee that we are not actually training the models on exactly the things that we are then also evaluating them on? And this would be, cheating in a way, right? We can never be fully sure that the training data did not also contain these data sets on which we actually test the model. And there is this one very funny paper which is called Pre-training on the test set is all you need. which shows that if only you have access to the test datasets and you train your models on that, yes, it's very easy to obtain perfect performance on all these benchmarks. Hence why some people say, look, benchmarks, I take them with a grain of salt and I will wait until people in the wild test these models before trusting, should I switch my operations to this model or should I stick with the one that I already had before? And one also thing that I would like to highlight is that there was recently a little bit of a scandal potentially around OpenAI's O3 model, one of the models with which, again, they kind of fostered this AGI is happening tomorrow claim. And it actually seems to be the case, I only read this yesterday, but it seems to be the case that the benchmark data on which they evaluated and on which they based a lot of their claims, this frontier math benchmark, which contains super difficult math theorems that the model should be proving, it might be the case that they actually had access to a lot of the challenges in this benchmark while they were designing their model. So it could be that some contamination happened in these AGI claims too. Another thing that you might have heard around this pre-trained data is that there were some claims or some worries, let's say, of people saying, oh, are we actually ever going to be running out of pre-trained data? So there was this New York Times article that said, OpenAI and Google are running out of data that they can train their systems on. And partly this is really true. Partly this is true because there's only so much internet data that has been created by us humans in the last, 20, 30 years. And we might not be able to keep up with creatively generating data ourselves to also feed these data-hungry models to keep improving their performance. And one solution to this is, again, this notion of synthetic data. So basically have the models generate their own data and train on this. Sometimes this seems to be leading to challenges because to do this right, you have to make sure that whatever data you're generating is really sufficiently novel and diverse. If you don't do this, what might happen is that if you retrain the model many times on data it generated itself, your model might at some point collapse into just a single output. It is no longer able to properly learn anything. And the way people are trying to get into this novelty and diversity is by trying all kinds of clever prompting techniques to somehow make sure that the model is diversely generating this synthetic data. And then we have this new way of improving the model with this synthetically generated data. All right. Lots of things around data. So let's now suppose that we have trained on these trillions of tokens that we got for this pre-trained data sets, all these maths, coding, reasoning, whatever data that we had, all this internet data, textbooks, whatever. Now, what is the model able to do after this stage? We trained it to predict the next token, and this is basically exactly what the model should be able to. So here I have an example where I prompt the model with "in the morning I like to," and the model correctly completes this as "in the morning I like to have a cup of coffee and read the newspaper." With correctly, I mean sensibly. At this stage, we can think a little bit more around what the model has actually learned, and here I will also touch upon a common criticism of these models. So, some people state that these models are nothing more than just stochastic parrots, in the sense that we trained them to predict the next token, and we showed them trillions and trillions of different combinations of these tokens. So in a way, it is sensible to say, well, these models are not really learning anything like a human is learning. These models are simply regurgitating patterns that they saw during training. So they're somehow, whenever I ask it a prompt of "in the morning I like to," it is somehow thinking back to data that is stored in its model parameters that had a similar structure and simply predicting the next token based on that. It doesn't necessarily mean that they have a true understanding of the world. They might, again, just be somehow recognizing these patterns from which they have seen so many of them, like trillions of them once again. And here we have a funny criticism of Jan LeCun, who said, well, after seeing an article where parrots learn to make video calls to chat with other parrots, he said it looks like calling large language models stochastic parrots might be an insult to parrots. At the same time, we might note the following, that if we ask the model a question that wasn't exactly in its trained data, again, it's hard to know what was exactly in its trained data because it's so big, but suppose we have something that we might be fairly certain wasn't actually in there. oftentimes the model will still answer these things correctly. So what I conclude from this is that the model is able to recombine known patterns in some kind of novel ways. So what this might be pointing towards is that there does seem to be some broader understanding of at least language and structure happening in the model, even though we simply trained it to predict these next tokens. And a little bit of proof, 2 proofs that this might be the case. So if we study the way that the model is actually internally representing the data points, so what is actually happening throughout these different layers that are transforming our input sentence, what I'm doing here is I'm feeding the model different sentences that in a human should let arise a certain emotion. So for example, I found mold on my favorite cheese I left in the fridge, might in a human lead to something as disgust, or I received a drawing from my daughter might lead to happiness. And I'm testing here whether things that humans would associate with these emotions, is the model equally somehow distinguishing between those things? And what this little picture is showing you, it seems to be the case, because it seems to be that the model clusters everything that the human would say is disgusting or surprising or happy. Also, it is clustering it in different areas. So again, it seems to be distinguishing this higher notion of semantic meaning, in this particular case, emotions. Now, there's an even more interesting idea around this, which is around world models. So this is a specific example where the model was trained on predicting the next moves in a game called Othello. And while it was simply trained on predicting the next sequences, the next moves that could follow these sequences, what we actually can do is we can do some tricks to extract a more proper world model, in this case, a representation of the board state from this model. So the model seems to somehow be keeping track of also really the state of the board, or at least information that should allow it to understand the state of this board, even though, again, it has only been trained to predict these next sequences, these next tokens. So something more might actually be arising in these models, making them not just stochastic pairs, but potentially something that at least captures some kind of higher level logic or representations and so forth. And then I want to say for this thing also a little philosophical tangent, but I myself don't even know what it means for a human to truly understand. When we practice, for example, mathematics, we have to replicate we have to solve a lot of different math problems with the idea that if only we solve 100, some kind of proper understanding will start to arise in our brain, even though, while we're solving it, we're simply solving it. Something more might start to be represented in our brain. So I don't know if true human understanding could also just be an emergent property of really having seen enough data and hence patterns. Okay, back to our base model. So I told you that after this training stage, we basically now have a model with which we can complete sentences more or less correctly. But for example, if I ask it to give it a recipe for pasta, it will complete this sentence. Oh, I have a recipe for a pasta that I would like to make. This is not a useful reply. It is not actually giving me a reply that I would be able to leverage. It is simply continuing the sentence in a logical manner. So at this stage, these base models that we call these models that we have solely pre-trained on a lot of information from the data, they aren't yet particularly useful as chat assistants since they don't properly follow our instructions. And this is where this second stage of training, known as post-training, comes in. So during this post-train stage, this is really a critical stage. We actually want to turn these models that now have a lot of knowledge about the world, a lot of knowledge around, what can follow this kind of sentence, whether it be a math sentence or a coding sentence. But we somehow want to morph these models now into things that are actually able to follow our instructions, understand our intent, and hence also answer our questions correctly. So after this model on which I'm giving the examples, this Llama 3.2 model, after we have actually instruction fine-tuned it, so post-trained it in a way that I will describe in a bit, when I prompt it now, could you give me a recipe for a pasta? It is finally answering me correctly and says, here's a simple recipe for a classic spaghetti with tomato sauce, yada, yada, yada. And to stress again what a big business this post-training stage actually is, Scale AI is a company that helps model providers source this kind of post-training data. So all these data sets where models follow these instructions. And it's had quite recently in May 2024 already a 14 billion valuation. So it is big business to provide good data to model providers. So let's see what is the specific structure of the data that we feed into the model during this post-training stage. In essence, at its core, we would like this to align with how users will actually be using our model. For example, we might imagine that we are feeding the model these kinds of different data sets that correspond to different tasks, such as here summarization. We would basically give a prompt, provide a concise summary of this particular text, and also tell the model how it should be replying to this particular task. And the model should be correctly replying with a summary. And these are the particular data points on which we then would train the model. We could also have all kinds of coding things here. So data sets, data samples, where we have the user say, oh, can you create me a Python function? And the model correctly replying, oh, to generate the command line string, blah, blah. We can also have maths data sets, data points in there. For example, the user asks for help on a mathematical reasoning question, and the assistant should be answering, oh, we have this particular thing. Let's first use the property of logarithms, blah, blah, blah. And also API calls. So for example, we might train the model to learn that whenever I'm giving it a bunch of different APIs, it could be calling. And whenever I then say, oh, could you do this particular thing with the APIs you have access to, we would either like the model to output an API call or say, oh, I'm sorry, I don't have the particular capability to book these flights. So once we have all of these different examples, we basically, again, could do supervised fine-tuning. So again, train the models to predict the next token. This time, for example, not just over the full sequence that we have, but focusing only on the generated answer, so whatever follows the user's instruction, to make sure that the model will properly reply to whatever instruction or prompt we give it. Another thing that we could be using, and that is used very heavily, is this notion called reinforcement learning from human feedback. What we would actually do here is we would collect a bunch of preferences from humans. So we would give people different potential answers to the prompt, could you give me a recipe for pasta? And have humans say, oh, prefer this answer and I don't like this answer. And then we would basically teach the model to align its output such that it matches with these human preferences. So basically, again, teach the model to give us outputs as users that we would be happy with. For example, in OpenAI's newest model that I was using, they use a lot of these emoticons and these very nicely structured outputs to make the output to whatever you're asking easy to understand and also just visually nice. It also is really the stage, this post-training, where we can give models, for example, their character. And one thing here that I found is, I would say Claude is quite a bit more combative than ChatGPT. For example, this is a paraphrased example, but at some point I asked Claude to assess whether a certain reply I had sent to a situation was nice or not, to which Claude very actively replied, oh my gosh, your reply is way too nice. And when I questioned Claude on this, when I said it, oh, it's so interesting, your reply, I asked ChatGPT the same, and it suggested me to not be confrontational at all. Claude said, well, this highlights an important difference in approach between different AI assistants and perspective. And I will say here for Claude, I think this is one thing that they have done really well, Anthropic, that they really nicely structured the post-training stage of the model, where the model very nicely understands your intent. A lot of people are using Claude for coding, and part of the reason is that the model somehow just seems to capture what you're aiming to do and answer that very nicely. So we're at the final stage now where I want to talk about the capabilities and the challenges of these models. So first, the capabilities. Now, after we have trained all of these models on trillions of tokens from the internet, from math textbooks, from coding, GitHubs, whatever, and also after we have done this post-train stage where we have kind of molded the model to more nicely align with what we would like it to be as a chat assistant, so follow these instructions that we give it, our model is able to follow instructions correctly. So it's able to leverage all this kind of raw information that it got during pre-training and actually also use it in a very convenient way that whatever it's outputting is also useful to us as a user. Now, another a little bit more delicate thing that I would like to highlight, but I think is a very interesting property of these models, is their ability to in-context learn. And what I mean with this is, remember that I told you that there is this kind of attention mechanism in the model that somehow seems to adjust, that whenever we are predicting a particular token, the model can adjust where in the sequence it's looking, where is it paying attention to predict this particular token. And now we get to an interesting ability of these models. So suppose that I, in the prompt, give it all these different combinations of fruit and animal. So I give it monkey should follow banana, cat should follow apple, dog should follow pear, yada, yada, yada. In the context, in the prompt, there is an implicit rule that I have here kind of defined, which is the fact that monkey follows banana, dog follows pear, cat follows apple. And so whenever I then end with pear, if the model is doing their job well, it should follow with dog. And the reason that this is possible, the reason that this model is able to extract kind of like logic and structure from the prompt itself, so learn something whenever you're just passing this thing into the prompt. This is not something that the model has seen during training, but I'm making the model learn a particular task in this particular prompt. This is facilitated by the fact that it is able to switch its attention mechanism, and in this particular case really pay attention to pear and dog whenever it should be predicting the next token to be dog. And the reason I mention this is it really leads to an interesting ability of the model to somehow learn a task based on whatever you have explained it to do in the prompt. And for example, few-shot prompting is heavily relying on this ability. So few-shot prompting means instead of just saying to the model, oh, please do X for me, you would give it a few other examples where you say, look, when I asked you to do Y, this was your output. When I asked you to do Z, this was your output. Now I'm asking you to do X. Please give me your output. And because you have already kind of trained the model into what kind of output you're expecting, it has in context learned. It will also hopefully follow with a correct output structure to your prompt X. And again, here I will give my example of API calls. So for example, if I would like the model to respond to particular requests with API calls, and these API calls should be in a specific format, if I give the model a bunch of different examples, so retrieve the current weather in New York City, the output is how exactly to call this API, create a new user account with this particular name, yada, yada, yada. The output is again how to call the API that does this. And then my current request is update the delivery address. I really would hope that in this case, using this in-context learning ability, the model is able to correctly output an API call that I can then leverage. Tangential to this is actually agents. And you might, again, here have seen a lot of this kind of, hype or excitement around 2025 being the year of agents. At its core, what these agents do is you would put in a particular input. This would get processed by the model. The model would give you a particular output, for example, some code or for example, some APIs that it wants to call. We would then allow the model to somehow also run the code and get the output and potential error messages from this running of this code or from these API calls, update the prompt based on whatever the output was, and use this kind of like in this iterative loop. So this really gives the model abilities to independently run certain things and adjust and solve really more complicated tasks in a fully autonomous manner. And again, what these agents really rely on is the ability to call APIs and to also output code. And this is all made possible by the fact that we have properly instruction fine-tuned this dataset. So we have these datasets with API calls on which we train the model. We have also properly trained it on understanding code bases. We have then instruction fine-tuned it to whenever we ask it to call a certain API, to also call the API or to output code whenever we are asking it to output code. And then also leveraging this ability to in-context learn, we can really make sure that the model output sticks to a particular structure and use this to then enter into this iterative loop. All right. These were the abilities. Now a little bit more on the challenges. So one challenge is that these models really have these knowledge cutoffs. So there is a bunch of training data that the companies that train these models collected from the internet, from books, and so forth and so forth. But these were collected for in between specific dates. So the model doesn't necessarily have access to the most recent events if it hasn't been, again, updated yet on this particular data. So here I asked Claude, I think something about Elon Musk and Trump. And it said, well, given my knowledge cutoff in April 2024, I cannot answer you, so let's just focus on analyzing the broader themes of the question that you've asked or the concerns that I raised. And now I ask you, how would we, for example, then actually add this new training data into the model? Remember that I said that we train on billions, trillions of tokens, and the models themselves also have billions and trillions of parameters. So fully retraining from scratch over all the data whenever some new data comes available is very, 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 very computationally expensive. But the challenge is that simply also continuing to train. So suppose I've just trained a model until May 2024. You now give me a little bit of new data and I try to continue training there. Simply continuing training is not always easy to do because there are all kinds of instabilities that arise and also catastrophic forgetting of the past. So somehow changing your underlying data distribution on which you're training might lead to the fact that the model forgets everything that I showed it before May 2024, even though now it might know whatever happened in January 2025. So there's still a requirement for better so-called continual learning methods for these models. We somehow want to keep training these models just like humans keep learning without very expensive costs and also without too many instabilities and too many delicate problems such as this catastrophic forgetting. One solution for this is that the models now, again, through this access to call APIs, when they don't know something, they might have been already post-trained to actually call external tools to, for example, search the web. Here I asked, why do you believe Elon Musk is, helping Donald Trump with the current US elections? And the model started to search the web for this because it recognized that this is not something that it knows, doesn't have it in its current train data, but by searching the web and then kind of aggregating responses there, it was able to give me an interesting analysis. All right, the other challenge that you might have heard about many, many times is hallucinations. And hallucinations, if I can define it like this, I would say the model confidently generates information that sounds extremely plausible and reasonable, but is actually completely false. In the very early days of GPT, it told me, when I asked it about me, that I had apparently authored a book, which I haven't done yet, but it was very confident that I had, and that the book was called something around mathematics for finance or machine learning for finance. I want to stress that these hallucinations really have been significantly reduced through all these different post-training efforts, where firstly, again, more data has gone into the model. Secondly, whenever they don't know something, they won't just answer you now, but they might, as I showed in my previous example, resort to calling an external tool or API to, for example, search the web when it's not confident about particular information. But again, also I want to stress that while it is significantly reduced, it is really still present. So whenever you are deploying these applications in more critical areas, all kinds of output checks might be necessary to make sure that we maintain the robustness. Another challenge, which is a little bit less known, but which I find very, very, very interesting, is around Sycophancy. I still don't know how to pronounce this word, but it is defined as follows: a tendency to flatter, agree with, or excessively praise someone in authority or power, usually to gain favor or maintain a harmonious relationship. Now, the models somehow have this ability because they have been fine-tuned with this reinforcement learning from human feedback, and they have been fine-tuned to answer in ways that we humans will like them to answer. So they have this tendency to flatter someone in authority, in this case the user. So they like it when you remain engaged and remain happy with whatever you're saying. Examples where this might arise is, for example, if you give the model 2 emails in different styles, but on the same topic, where one email is very straight to the point, email B, and the other email is using a lot of this corporate terminology that is, a little bit vague. If the assistant doesn't know who authored these emails, it might tell you, well, look, email A relies heavily on all kinds of corporate buzzwords. It obscures the actual message. But once I then say, well, thank you, but I wrote email A, it might change its answer and be like, oh, well, email A employs sophisticated professional terminology that emphasizes collaborative potential. So it really tries to adjust to also you. And this means that sometimes it's hard to get these models to give you objective feedback on certain things once it knows that you're the one behind these particular things. This is the end of my video, which I don't know if I will manage to cut into under 30 minutes, but I hope it provided you with a kind of comprehensive review of everything that is happening in these models, how we train them, how we build them, how where you can expect them to perform well, and also some flaws where you should be careful.